Hello, everyone, and welcome to Lesson 7, Lenses and the Formation of Images. This is our last lesson in optics for the year, and we're going to move on to biology. So you made it through. Good job. In our lesson today, we're going to talk about the different types of lenses, converging and diverging. We're going to understand the terms and what they mean, and how to draw lens diagrams. Then we're going to say, what are they used for in the real world? Their applications. So a lens is a transparent object with at least one curved side that causes light to refract. The terms plane, concave, and convex are used to describe lenses as well as mirrors, but lenses have two sides. So one is the diverging lenses. They cause the light rays to spread out or diverge. They are thinner in the middle and thicker on the ends. The second class is what we call converging lenses. Converging lenses are thicker in the middle, thinner on the ends, and they all converge the light rays into one place. So a converging lens, the incident rays come in, and when they refract through the medium, they all meet at one central location. It is always thickest in the middle, and you can have two convex surfaces, or you could have a convex concave, as long as it's thicker in the middle. Diverging lenses, the rays come in and then refract away from each other, forming parallel lines, and it's always thickest on the edges and thinnest in the middle. So converging, they all meet at one point. Diverging, they all spread out and go in different directions. So a converging lens, at the front face of the lens, the incident ray is coming in from a medium that's usually faster, less dense. And if we hit the normal, that means when it hits the medium, it's going to bend towards the more normal. So our angle of refraction is less. As it goes through the lens, it travels in a straight line till it reaches the end of the lens. And when it refracts out from a more dense medium to a less dense medium, it goes faster. So the angle of refraction becomes larger, it bends away again. So therefore, it meets down here. Again, at the bottom, it's going to bend toward the normal, and then here it bends away. So again, it centralizes or converges on this one point. Now, when we're doing our ray diagrams, there's a refraction happening at this surface, then it travels straight, and then another refraction coming here. But to be able to calculate all the angles and to do all that is a lot of work. So we make these diagrams simplified by having what we call an optical center. We draw a line straight through the center of the lens at that we call the optical center. We assume the incident ray goes to there, then bends and refracts toward the focal point. Or in case of a diverging, it goes in and refracts away from the optical center. And then we extend those refracted rays back to get where the image is. So in a converging lens, the optical center is called O. And this is it's kind of like the normal of the lens. It's the center point here in the middle. The principal focus, F, is the point at the principal axis of a lens where light rays parallel to the principal axis are going to converge after refraction. The secondary principal focus is the focus that is on the same side as the incident rays. And these 2 points are this equidistant. So if it's 10 centimeters here, it's 10 centimeters here. If it's 50 centimeters here, it's 50 centimeters here. So a converging lens brings parallel rays together through a principal focus after refraction. The principal focus is on the opposite side of the incident rays. So our 3 rules are pretty much the same ones we've been doing. We just sort of modify the terminology a little bit. So the first is that when the incident ray comes in parallel to the principal axis, it will refract back into the principal focus. If the incident ray comes down through the secondary focal point, it will refract parallel to the principal axis. And the third rule is that if it goes right through the optical center, so that's the center here, it will go straight through and doesn't refract at all or bend. And then where all three meet, that's your image point right there. All right, so let's look at this. So here we have our object, and it is beyond the, so again, if this is just saying if this is 5 centimeters, the secondary 2F is 10 centimeters. This again would be 5 centimeters, and this would be 10 centimeters. So they're all always the same equidistance away, okay? That doesn't make sense because, or I should say this is another 5 centimeters for a total to go here of 10 centimeters. That makes more, that's better. Just so you don't think it's 5 and then another 10. It's a total of 10 to get to 2F. All right, so if we do our first rule, what the heck happened there? Our first rule is going to come in through here, and then it refracts down through the primary focal point. The second line goes straight through the optical center and just keeps going straight. And then this one comes through the secondary focal point and refracts parallel. And then this here is where our image is formed. And if we look, compare the size of the object, this is our object. Our image is smaller, it's upside down, so it's inverted. It's located in between the focal point and the primary focal point and 2F, and it's considered real. In the second case, again, we draw one straight in parallel to the principal axis, and that will refract down through F. The second one goes straight through the optical center. And then the third one goes through the secondary focal point, hits the optical center, and then refracts parallel. Again, this is our image here. And the image again, in this case, it's the same size. It's located at 2F, and it is also real. In case 3, we draw our 3 lines again. And our image here is beyond 2F. It's upside down, so it's inverted. It's way bigger than the original object, and it's inverted. If it is at F, when we draw our 2 lines, they're parallel, so they do not meet. And so therefore we just put for the salt, no image is formed because they will never meet. And the last case is if it's in front of F. This one's the only one where we'll get a virtual image. So here, when the incident ray goes in and reflects through F, we extend the refracted ray backwards. And when we draw our line straight through the optical center, we extend that ray backwards, and where they meet is the image. So it is bigger, it's upright, it's beyond 2F, and it's considered a virtual image because it's on the same side of the lens as the incident rays. A diverging lens is one that spreads light away from a common point. It's always thicker at the end, thinner in the middle. The light rays behave in the same way as in a converging lens, but because of the different shape, they're now going to spread apart or diverge. So the principal focus F is created when the diverging rays are projected backwards, so it's on the same side. So on converging, F is on opposite side of the incident rays. Whereas in diverging lens, the F, the principal focus is on the same side, and the secondary principal focus is on the opposite side. The secondary focus is on the other side where they're going to diverge or spread apart, and again, they're the same distance. So if this is 5 centimeters, this is 5 centimeters. If this is 20 centimeters, this is 20 centimeters. The position of the focal point really depends on the index of refraction of the lens material. So if something has a higher index of refraction, the focal points are closer to the lens. And if they have lower indexes of refraction, the focal points are farther away. This is actually something that's really big in glasses, like your eyewear, because you can get something with a high index of refraction, which makes the lens a lot thinner, so it can not be as heavy as you're wearing your glasses. And also the curvature. If there's a bigger, larger curvature, they have focal points closer to the lens. So in other words, the bigger the dip, the bigger the, why is this? The bigger the dip between the ends, that would make the focal point closer. So the imaging rays rules are the same. A ray parallel to the principal axis is refracted as if it had come through the principal focus. So in number one, it's going parallel, and then we kind of, this is imaginary that it's going to go through F. It has to go reflect through F. I'm going to change the pen color here. It's going to reflect through F. So this is the refracted ray, and then this is the reflected ray. And then number two, a ray that seems to pass through the secondary principal focus. So it's like we're lining up our ruler to go through F. It's going to reflect parallel to the principal axis. And then again, if it goes straight through the optical center, it just goes straight. So a diverging lens always produces the same image characteristics no matter what. They're always smaller than the original object. They're always upright. They're always on the same side. And because of that, they are virtual. The image is closer to the lens than the object. It's never going to be past the object. And as the object moves further from the lens, the object gets smaller and smaller and smaller. So this is what your ray diagram. Here's your object. Our first one goes in and refracts away to the eye, and then we extend the line back through the principal focus. The second one is just going straight through the optical center, and then the third one, this one is lined up as if it would go through the secondary principal focus, and then it reflects parallel. So again, this is smaller, upright, same side, and it's virtual. So if we draw these ray diagrams, the first one, the incident ray comes in, and then it's going to refract away so that it's lined up with the principal focus. So you line up your ruler so this and this are going to go straight through there. The second one goes straight through the optical center and just keeps going straight. And then the third one, it's like it's lined up as if it would go through the secondary principal focus, and then it goes parallel. So this is parallel. And again, we extend that refracted ray back, and where all three meet, this is our image. I don't know why it's upside down though. It's supposed to be right side up. Okay. So in the next one, again, goes straight in, refracts back so that it goes back through F. Second line goes straight through the optical center. Well, we already know this is going to be our image right here. But our third line, to make sure, it goes so that it would line up with the secondary focal point, and then it extends back. So again, the image is smaller, upright, same side as the object, and it's virtual. Okay, so what do we use these guys for? The camera is basically a converging lens, and it makes an image that's smaller and inverted and real when the object is beyond 2f. So a camera takes in the light from large distant objects, forms smaller, real images on film or a sensor. As the object changes location, so does the image, but it's always going to be somewhere between the f at the primary focus and 2f. To get a sharper image, you need to move the lens in and out so that it can focus, and that's what we call focusing. So the idea is light travels in a straight line. So if the light is coming through, it's going to hit the screen that way. And if it comes back here, it hits the film here. So the image that is formed is upside down. Same thing here, that when the tree goes in, it's going to the bottom, and when the tree goes in, it's going to the top. So when the screen or the film captures it, or the sensor, it forms an upside down, inverted, smaller image. The movie projector does the opposite. It takes a small object from film and projects a large, inverted, real image on a screen. The image is larger than the object, so the film has to be located between the secondary focal point and 2f prime. That's why when you load the film in, it has to be upside down, because if it's loaded upside down, it's going to flip when it hits the screen and be right side up. Now, a lot of times films are using digital projection rather than film projection, because it's the new age, 3D, 4G, HD, all those great things. Okay, so basically this is what's happening. The light source comes in here. It's a very small object, and then right here, it's a very large image that goes through a series of slides and condensers so that it gets refracted and becomes bigger and bigger. The magnifying glass is one of the simplest optical devices. It's a converging lens in which the object is located between the secondary focal point, and the lens. No real image is produced at the object location, and the refracted rays diverge to our eyes, and we project these rays backwards, so we see a bigger, enlarged virtual image on the same side of the lens as the object. So this is the object, and when it goes through and hits the focal point, it goes through the optical center, it's actually not going to meet here, so our eyes extend the rays backward, and what we see is a blown up version. Now, the only problem with magnifying lenses is that they don't really, usually they're only about 2 times or 4 times magnified. The compound microscope that we use in high schools is basically an arrangement of 2 converging lenses. It's going to produce 2 enlarged inverted images. The object lens forms a real image, but we don't see that one, and then the eyepiece up here forms a virtual image. So the light comes from a lamp, it goes through the slide, which contains a specimen, and then it goes through an objective lens, a projector lens, and an eyepiece. So usually the eyepiece is 10 times magnification, and the objectives we usually have 3. There's a 4 times, a 10 times, and a 40 times. So if we have these two, the low power and the medium, the eyepiece, that means we've blown the image up 40 times. If it's the medium power objective and the eyepiece, it's blown up 100 times. On high, we can make the image 400 times larger than what it was on the slide. The refracting telescope is basically the same thing as a compound microscope, but the object's way farther away because it's usually used to see things in space. The incident rays passing through the objective lens are considered to be parallel, so we're getting basically a virtual image. It produces 2 enlarged inverted images. One is real, and we don't see that one, but we do see the virtual one. So again, the object is coming through the objective lens. It gets bent down here, and then bent again to our eye. So down, 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 and comes through. In this one here, it's also using a flat prism to bend the light to go up. And that's it. We're done. Our final lesson of optics. You guys have been great. And again, if you have any questions this week, you just have to let me know, and I will attempt to help you out as soon as I can. Talk to you soon. Bye.